Good morning, everyone. I'm standing before the coffee break, so I will make sure that I will fasten this up. So imagine you're driving an autonomous car. The car meets an object on the road. In today's world, the collected data is sent to the cloud or a computer for inference. This process of sending data to a distant computer becomes a cognitive bottleneck when more and more data has to be collected and sent across the limited bandwidth for inference. This is also an accuracy issue. So the bottleneck here is the segregation of sensing, memory, and compute elements that creates energy, throughput, and bandwidth issues. So as a solution, we bring in the in-pixel computing paradigm. This is a practical and innovative solution that is built upon a novel hardware algorithm co-design technique to address the challenges. From the hardware side, we have embedded computation inside the pixel array such that massively parallel in-pixel analog multi-bit convolution operation can happen. This operation is supported by peripheral circuits such as column parallel ADCs. From a software side, in order to reduce the bandwidth, we modified the CNN algorithm used for object detection and tracking. So we used large filters, strides, optimized number of channels, and optimized batch normalization layers. So I want to again highlight that rather than independently modifying the hardware or the software, we used co-design technique to reduce the convolution layers before sending the data to the backend. So our approach is very similar to the BioVision, where initial inference is done at the retina before the signals are sent or transmitted to the brain. So the hardware implementation can be done in high-volume manufacturing, either on a monolithically defined technology node or as represented in this slide, where we can use 3D heterogeneous integration where we do one-on-one mapping of the pixels with the memory. So to realize the in-pixel computing, we must integrate the front-end and back-end platforms. So the back-end FPGA receives the data from the front-end sensor layers and accelerates the remaining neural network layers. So we built a synthesizable framework from PyTorch to elucidate the PPA metrics using efficient FPGA bit streaming. And we use this platform to evaluate practical demonstrations of the in-pixel computing paradigm. Now, in the next few slides, I have video demo to demonstrate the benefits of the in-pixel compute. So this is the first video. This is the baseline video. And in this video, there is no in-pixel computing framework. So it's a complex city scenario where bikes and cars are moving. Cars are stopped. There are traffic lights, traffic stops, building on the sides. And onto this baseline, we implemented the in-pixel paradigm. And in the second video, we implemented the global tracking transformers. So as you can see, different colors represent different objects tracked across large and small frames. We are able to detect small objects such as biker, large objects, the cross traffic, etc. And we obtained 21.29 times improvement in energy delay product over the baseline. In this third video, we have added 5% noise to the previous tracking video. And we see that there is only 0.1% reduction in the mean ID F1 score. And in this final video, we implemented the intelligent frame skipping on the center track algorithm. So the top video is the baseline. Again, this is a complex city scenario where several vehicles are parked, bikers are on the road, and there are regions where lighting is dark. The bottom video demonstrates after frame skipping is implemented, and we can do a 13.3 times speed up when frame skipping is implemented intelligently. And finally, we not only limit our work on tracking data set, but also on other data sets, such as visual wake quartz, hyperspectral imaging, to name a few. And we see significant reduction in the bandwidth. And these bandwidth savings translates to the EDP savings. And we see that there is 10 times to 20 times EDP savings. So in a nutshell, in-pixel paradigm enables a wide range of swap constraint, complex machine learning tasks at the extreme edge. And finally, I want to thank my team, without whom I won't be standing here, Dr. Akhilesh Jaiswal, Dr. Peter Birel, Dr. Wael Al-Majid, Dr. Andrew Schmidt, and the students who have tirelessly worked and innovated to make this demonstration possible. I also want to thank once again DARPA for giving me this opportunity. I want to thank Dr. Whitney Mason, Dr. Brian Jacobs, and the team for mentoring and guiding us. Thank you.